Those small curved tips on aircraft wings, winglets, save airlines over $200,000 per year per aircraft in fuel costs. The mathematics behind wing design is so precise that changing the wing curve by just 2 millimeters can mean the difference between profitable flight and economic disaster. Here's the hidden calculus, geometry, and fluid dynamics that transform 500 tons of metal into graceful flight, and why the Wright brothers' wing design would fail catastrophically on modern aircraft. Aircraft wings must generate sufficient lift force to overcome gravity while minimizing drag that wastes fuel and limits speed. This seemingly simple requirement involves extraordinarily complex mathematics combining fluid dynamics, differential equations, and computational modeling that required centuries to fully understand. The fundamental lift equation L equals 1/2 rho v superscript 2s_L reveals deceptive complexity. Lift L depends on air density, rho, velocity squared v superscript 2, wing surface area, s, and the mysterious coefficient of lift c_L, a variable that encompasses all the intricate aerodynamic properties determined by wing shape, angle, and airflow characteristics. Optimizing this equation drives every aspect of wing design. The Swiss mathematician Daniel Bernoulli discovered in 1738 that faster-moving fluid creates lower pressure, the fundamental principle enabling flight. Pressure-velocity relationship. Bernoulli's equation P plus 1/2 rho v superscript 2 plus rho gh equals constant describes how air pressure decreases as velocity increases. Wings exploit this by creating faster airflow over the top surface than the bottom, generating pressure differential that produces upward lift force. Airfoil geometry. Wing cross-sections, airfoils, feature curved upper surfaces and flatter lower surfaces. Air flowing over the longer curved path accelerates to rejoin air traveling the shorter lower path, creating the pressure difference that generates lift. Angle of attack optimization. Wings operate at carefully calculated angles relative to airflow direction. Increasing angle of attack increases lift coefficient, but only to a critical point. Exceed approximately 15 to 18 degrees and airflow separate from the wing surface, causing catastrophic stall where lift suddenly disappears. Mathematical modeling. Modern wing design uses Navier-Stokes equations, partial differential equations so complex that solving them exactly remains one of mathematics' unsolved millennium problems. Engineers use computational fluid dynamics, CFD, to approximate solutions through millions of calculations. Winglets represent one of aviation's most successful aerodynamic innovations, demonstrating how subtle geometric changes yield enormous economic benefits. Wingtip vortex physics. Air pressure differential between wing lower and upper surfaces creates rotating airflow at wingtips, vortices that waste energy and increase drag. These vortices represent pure wasted fuel, converting propulsion energy into useless spinning air. Vortex drag reduction. Winglets disrupt vortex formation by creating vertical surfaces that block air from flowing around wingtip from high-pressure lower surface to low-pressure upper surface. This seemingly simple geometric addition reduces drag by 3 to 5%. Economic impact. A 4% drag reduction on a Boeing 737 saves approximately 200,000 gallons of fuel annually per aircraft. At $3 per gallon, that's $600,000 annual savings, making winglet installation investments pay for themselves within months. Geometric optimization. Winglet angle, height, and cant angle require precise mathematical optimization. Too vertical wastes potential. Too angled creates excessive interference drag. Modern split-symmeter winglets use complex curved geometries that optimize multiple performance parameters simultaneously. Most commercial aircraft feature swept-back wings, a geometric choice driven by high-speed aerodynamics. Transonic flow management. As aircraft approach sound speed, Mach 0.85, airflow over wings accelerates locally to supersonic velocities, creating shock waves that dramatically increase drag. Swept wings delay shock wave formation by reducing the effective velocity component perpendicular to the wing leading edge. Effective velocity calculation. A 30-degree sweep angle reduces effective perpendicular airflow velocity by approximately 13%. Cosine of 30 degrees equals 0.866, allowing higher cruise speeds before encountering transonic drag rise. Structural trade-offs. Sweep angle creates structural complications requiring stronger, heavier wing roots to handle bending moments from swept geometry. Wing design involves constant mathematical trade-offs between aerodynamic efficiency and structural weight. Boeing 787 sweep. The 787 uses 32-degree sweep, precisely calculated to optimize cruise efficiency at Mach 0.85 while minimizing structural penalties and maintaining acceptable low-speed handling characteristics. Modern transport aircraft use supercritical airfoils, revolutionary wing shapes that delay shock wave formation. Traditional versus supercritical. Conventional airfoils feature pronounced curvature that accelerates airflow dramatically, causing early shock wave formation. Supercritical airfoils use flatter upper surfaces with subtle curves that distribute acceleration gradually, delaying supersonic flow. Drag reduction mathematics. Supercritical airfoils reduce transonic drag by 15 to 20% compared to conventional designs, enabling higher cruise speeds or improved fuel efficiency at given speeds. This geometric innovation revolutionized commercial aviation in the 1970s. Computational design. Designing supercritical airfoils requires sophisticated computational analysis, solving compressible flow equations at millions of points. Engineers iteratively adjust geometry until computer simulations show optimal pressure distributions, avoiding early shock formation. Boeing 787 application. The 787's wings combine supercritical airfoils with composite construction, achieving 20% better fuel efficiency than previous generation aircraft through aerodynamic and structural optimization working together. Wings must perform across enormous speed ranges from 150 miles per hour landing to 550 miles per hour cruise, requiring variable geometry. Fowler flap mechanics. Flaps extend rearward and downward during takeoff and landing, increasing both wing area, S, and camber curvature. This changes the lift coefficient, C_L, by up to 100%, enabling low-speed flight with wings optimized for high-speed cruise. Slat aerodynamics. Leading-edge slats extend forward and down, creating slots that re-energize airflow over the wing, preventing stall at high angles of attack. The gap geometry and position require precise mathematical optimization. Configuration mathematics. An Airbus A350 landing configuration with flaps and slats extended generates nearly double the lift coefficient of clean cruise configuration, enabling approach speeds of 140 knots despite 250-knot cruise design optimization. Modern wing design relies on supercomputer simulations solving fluid dynamics equations. Mesh generation. Engineers divide wing surfaces and surrounding air into millions of computational cells, then solve Navier-Stokes equations at each cell interface, requiring trillions of calculations per design iteration. Optimization algorithms. Computer programs automatically adjust wing geometry parameters, thickness, camber, twist distribution, searching through millions of possible configurations to find optimal designs meeting multiple performance constraints simultaneously. Virtual testing. CFD enables testing thousands of wing designs computationally before building expensive wind tunnel models or flight test aircraft, reducing development costs and time while improving performance. Aircraft wing design represents applied mathematics at its most sophisticated. Centuries of fluid dynamics theory, differential equations, and computational analysis crystallized into shapes that routinely achieve what seems impossible, lifting hundreds of tons into the sky with remarkable efficiency. Every flight demonstrates mathematical optimization that balances lift generation against drag minimization, structural weight against aerodynamic performance, low-speed handling against high-speed efficiency, all achieved through equations, calculations, and geometric precision measured in millimeters. The next time you see aircraft wings during flight, Remember, you're observing physical manifestations of some of humanity's most advanced mathematical achievements. Curves and angles precisely calculated to transform abstract equations into graceful flight.